Hey folks, welcome back to Newton's Laws, day 2. Remember that we have spent one lesson and we're going to spend a few more looking at a really important equation, which is F net equals MA. What we want to be able to do in this lesson and still the next one is get really good at drawing little pictures, little free body diagrams, where we draw in only forces. And then the usual drill is to use said free body diagrams to calculate accelerations or forces, and then sometimes maybe a bit of kinematics. So I've got an example here that might help you do some of the homework actually from the last box. That number 9 and 10 that I said maybe we could do together on Zoom. Maybe we've had a chance to do this by the time you watch the video. If not, feel free to ask about it when we do touch base. We have got a 150 kilogram cannon firing a cannonball by applying a force of 3,000 newtons on the ball for a little over a tenth of a second. And then there's kind of a weird statement or question here. It says, find the final velocity of each. And it's like, well, what the heck? What are we talking about a final velocity of the cannon if we're just shooting the cannonball? And I'm hoping that by doing some practice and looking at these videos and trying out all the homework, that you will recognize this question. It's a special type of question. When you see something about the final velocity of each, this is an action-reaction forces question. Remember Newton's third law says that for every action force, there's an equal but opposite reaction force. And it turns out if you can identify a question as an action-reaction question, they're actually pretty darn easy, because what we want to think about is simply how the force of one pushing on the other is going to be the same in reverse. So here, I'm going to actually, don't worry about sketching the fancy cannon. Let's just draw the cannon and the ball. Let's do this. Ball, cannon. I'll draw the ball like that. I'll draw the cannon as a brick. There we go. Free body diagram, we want to put forces on these two things. And it turns out that there is things like gravity acting on the ball. There's the force of gravity acting on the cannon. There's a normal force acting on the cannon, right? The ground is holding it up and pushing back up. But we don't actually need to worry about those. We only are going to worry about the action-reaction forces. And that would look like this. If we have this cannon shoot the cannonball with a force of 3,000 newtons, to the left, that means technically that the ball is pushing back on the cannon with an equal amount of force. So there is also 3,000 newtons pushing backwards on the cannon. And in an action-reaction question, that's really the only forces we need to worry about. Once we've got those forces locked in, it's the same on both. I guess one of them would be negative and one would be positive if you want to be picky. But what you want to do is, for an action-reaction question, is run F net equals MA for both objects. The key being that the net force is the same. Again, if you'd like to put one of these in as a negative, you go right ahead. It doesn't really matter. The cannonball has a mass of 4 kilograms. You can solve for A. The cannon's much heavier. It's 150 kilograms. Solve for A. So you can see that even though they have the same net force acting on them, they're going to have very different rates of acceleration because their masses are very different. Now I think, let's double check, 3,000 divided by 4 I believe is 750. Yes, and 3,000 divided by 150, is that like 20? Hey! So acceleration 750 meters per second squared, and a rate of acceleration for the cannon much smaller, it's 20 meters per second squared. There's the new chapter 5 portion of this question, and now it's asking us to find the final velocity of each object, which means do some kinematics. And if it's okay with you guys, I'm just going to scroll down and just throw those numbers up there for you just to save time, because again, you can do kinematics in your sleep. There's kind of the picture I drew. There's the accelerations. You can see in these notes I made one positive, one negative. Doesn't really matter. And if you go to run the kinematics piece, there you go. The ball is going to come flying out of that cannon at 90 meters per second. But the cannon's going to recoil, right? We know that sort of, well, maybe you don't. Guns recoil. Cannons recoil. They have this backwards force. And it's because of Newton's third law, action-reaction forces. So the cannon itself would actually want to move backwards at 2.4 meters per second, which is why a lot of cannons, like in civil wars in the United States, they actually put them on wheels. And that way the thing would actually recoil backwards. If you were building yourself a pirate ship and you bolted the thing to your wooden ship, that would be bad. Because every time you fire it, the thing's going to want to recoil. It's going to want to rip itself off of whatever it's bolted to, which could leave you with a hole in the floor of your pirate ship. So now you know, the next time you go build a pirate ship to pillage, you have to account for that recoil. Give that gun some way of actually rolling backwards. All right, let's try another example. Doesn't quite fit in semester 2 time-wise quite as nicely as it did in semester 1. But let's find the distance required for Santa to reach his takeoff speed of 45 kilometers per hour. So we've got Santa here. We're going to draw a free body diagram. We're going to make him a blob. There he is. Santa and the sleigh, and we want to now list all the different forces that are acting on Santa. This is our free body diagram. Now you can see that we've got this Rudolph force, maybe I can call it that, the reindeer force pulling to the right. That's worth 7,000 newtons. And then we want to go through the other sort of usual suspects. What other forces are acting on Santa in a sleigh sitting on maybe the roof of somebody's house? Well, there's going to be gravity, m times g, and we know his mass. We know gravitational field strength on this planet is 9.8. So we can quickly get that number on our calculator. 5292. So there's that many newtons pulling down. Now let's assume maybe he's up on the roof of somebody's house. That means the roof is holding him up. He's not sinking into the center of the earth. And that upward force, the surface holding him, is the normal force. Now we know that the normal force is equal to the force of gravity because he's not accelerating up or down. So that's also 5292 N for newtons. And then you can see that they've given us this coefficient of friction here. That means we will have to account for friction in this question. So friction's going to fight against our reindeer force. I'm just going to move this picture over a little bit to give myself more room. And we can calculate that with the coefficient of friction times the normal force. And remember, we cheat. The normal force is equal to the force of gravity. The good news is it's already all labeled for us here. So that's 0.15 multiplied by 5292. Hit the calculator. 793.8 N for newtons of friction force pulling backwards. So that's our free body diagram, which is actually going to make or break this question for us. Maybe I'll go green, red and green, Christmas colors. So once the picture is done, and that's the busiest diagram you'll ever end up with in Physics 11, to have those four forces. The good news is if you look at the up and down forces, they just wipe each other out, right? We would subtract them. We end up with zero net force in the up and down direction. But if you look at the side to side direction, the net or overall force, there's 7,000 newtons of force from the reindeer fighting against 793.8 newtons of force from friction equals 540 times A. So if we subtract, think about net force not as a single number, but think about it as actually like an addition or a subtraction depending on the question. So I like to think about F net as 7,000 minus 793.8. I don't really care what the answer is, which is going to come out right here. 6206.2. I want you to think about it as a subtraction because the two forces are fighting each other. equals 540 times A equals, let's see, 11.49 meters per second squared. So there's your rate of acceleration, which is still not the end of this question. I'm actually going to scroll ahead. We now need to do some kinematics. Easy. Do watch, though, that if we're going to do some kinematics, we do have to catch the 45 kilometers per hour. There's our acceleration, and there's the kinematics again. You can do it on your calculator if you want. But do notice that the final velocity, divide by 3.6 comes out at about 12.5 meters per second. You end up with the distance required, 6.80 meters. Okay, example 3 of 4. Here we've got a lunch bag, and we're told that it can apply 52 newtons of force to a 4 kilogram lunch. That's closing in on 9 pounds of food for the day. That's a big lunch, but let's not judge. A 4 kilogram lunch before it rips. If the bag is pulled up with an acceleration of 5 meters per second squared, will it rip? So maybe let's imagine your parents have packed you a nice big lunch, sitting on the counter. Maybe you're rushing out the door to catch the school bus or catch a ride to school, and you grab this bag and you accelerate it up really quickly. Is it going to rip or not? That's what we're trying to figure out. So I'm going to draw your lunch like that, just a blob. It's 4 kilograms. I'm not going to put that in my picture. Remember these free body diagrams, we just put forces in there. So in this case, what forces are acting on the bag or your lunch in the bag? We could say, hey, gravity's going to pull down on the bag, m times g. And we know this is a 4 kilogram lunch. So 4 times 9.8. 39.2 newtons of force pulling down. Now here, you're pulling up. There's like the force of your hand. And I'm going to draw that arrow as bigger. We know that the upward force has to be bigger because we do have a positive acceleration. So that means we do end up with some net force pulling upwards. You don't have to be that picky when you draw free body diagrams, but I will, just because we can. The 52 newtons is actually not how much force you pull with. We don't actually know what the applied force is. So I'm just going to put it in there as FA. 52 newtons is just what we're going to compare the applied force to see if the bag rips or not. So we're pulling upwards with some unknown force. We don't know what that is yet, but that's okay. Let's just leave it as FA. And that's actually it for the diagram. There's nothing happening side to side. So we can move into F net equals MA. And we have to figure out what is our net force. What's our overall force? Well, in this case, we've got an upward force fighting against a downward force. So we're going to subtract them. And I always like to, when I do the subtraction, do like winners minus losers. So I know the applied force is bigger, excuse me again. So I'm going to take the applied force minus the force of gravity. 39.2 equals, this is kind of weird because usually we know the two numbers that go in the F net side of the equation, but just watch what's going to happen. There's something kind of cool. FA minus 39.2, shoot, we don't know what that applied force is. But what is cool is we know the mass. We've got a 4 kilogram lunch. And this time we're actually given a different piece of information. We're given the acceleration. It's 5 meters per second squared. That's usually the unknown. So hopefully you can look at that equation and say, hey, that's cool. If we're trying to find or solve for the applied force, that's easy. All we have to do is add 39.2 to both sides. So a little twist in this question, but it actually works out really nicely. 5 times 4 is 20 plus 39.2. That means the applied force is going to be 59.2 newtons. And if we look back, the bag can only withstand 52 newtons. So unfortunately, 59.2 newtons is bigger than 52 newtons. And this bag, well, it rips. Lunch scattered all over the kitchen floor. All right, let's try one more example. This is fast and furious, so if you have any questions, remember, hit me up on a Zoom session or email me. Here we've got a 1,500 kilogram Indy car going 300 kilometers an hour. It spins and slides out of control with a coefficient of friction of 0.60. That tells us we're not going to be able to ignore friction. We'll have to put it in there. We want to know, this thing's like skidding out of control. How far does it slide until it comes to a stop? That's really what we're looking for. So what we're going to want to do is draw our little Indy car. That's just like kind of a Formula One style race car. I'm going to draw it like that. There it is, a nice blob. What forces are acting on a skidding car? And this is a pretty classic example. I should throw that in there. Anytime you see a question about skidding cars, they're set up the same way every time, and there's probably like 3 or 4 of them in your homework questions. So this is a good one to go over. What forces act on a car if you're skidding? Well, there's gravity. So that's a force that we know. 1,500 times 9.8. Might as well find the number if we have it. 14,700 newtons of force pulling down. But the car's not getting sucked into the center of the earth because the road is pushing back. And that's the normal force. And we know it has to then be the same as the force of gravity. 14,700 newtons. We've got some friction that we can't ignore. They're giving us a coefficient of friction. Shoot, I gotta move this over. Give me 2 seconds. There we go. Force of friction is equal to the coefficient of friction multiplied by the normal force. We've got the coefficient. We already found the normal force as 14,700. Grab the calculator. 8820. N for newtons. Now, here's what's kind of crazy. When you hit the brakes in your car, is there anything pushing your car forwards? And take a minute. This is where students go, well, yeah, because the car is moving forwards. No, 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 no. Don't think about the car moving forwards. Think about if there's anything pushing the car forwards. Right? You've taken your foot off the gas pedal and you're just stomping on the brake pedal. It turns out there is no forwards force. So sometimes students will want to put this in. They'll want to say, hey, there's got to be some forward force because the car is moving forwards. But there is no forwards force. There is no applied force forwards. That is gone. And you might go, well, what the heck? How is the car moving forwards? Well, I agree it's moving forwards, but it's decelerating. That means we have this backwards force winning out because there actually is no forwards force. So in a skidding car example, when you step on the brakes in your car, there is no forwards force. Our free body diagram actually looks like that. Which actually is kind of nice because when you go to run the equation, F net equals ma, what is the net force? Well, your downward force and your upward force, they're equal but opposite and fighting each other, so they cancel out. And that means the net force for a skidding car is actually just the force of friction, which is pretty darn cool. So this is a special case. You can't always say this in any question, but for a skidding car question, the net force, it is the force of friction. So pretty slick. It's 8,820 newtons. And I guess if you want to be picky, you could put it in as a negative because we do want to come up with a negative acceleration. The thing is slowing down. So if I take that answer and I divide by, I'm just going to throw a negative sign on it, sorry. Negative 5.88. So that's how quickly it's slowing down. It's losing almost 6 meters per second squared. And then this question says, how far does it slide? Okay, so we need to do some kinematics. We will need to catch this. The initial velocity in kilometers per hour isn't going to work. We're going to have to convert that into meters per second. And again, you can do kinematics all day long. You could pause the video here and race ahead and, get it, race ahead. Sorry, bad physics joke. You could go and calculate the number before, or you could just watch me do it here with the page down. There's what an IndyCar looks like, by the way. There's our negative 588. Don't worry about what happened there with M disappearing. There's our final answer. 591 meters. Now I want you to think about that a little bit. 591 meters. That's a long ways. That's like more than half a kilometer, right? So let me go back here. The distance was 590-ish meters. Was it 91? I don't remember now. That means, think about us sitting in our physics classroom again. An IndyCar goes ripping past the school at 300 kilometers an hour. If they hit their brakes on Eckert Street, heading down towards West Bench, going down the hill, they would skid for about 600 meters. That means if they locked up their tires and they were skidding and there's smoke coming off the tires, it'd be kind of crazy. They would stop when they were getting close to the Adidas Sportsplex. And I know there's a curve in the road there, so ignore that. But they would be pretty darn close to the Adidas Sportsplex before they stopped. That is a long, long way to skid out of control. And that's actually why speed limits are not 300 kilometers an hour. It has nothing, or I shouldn't say nothing, it has less to do with your ability to drive or pilot a car going that fast. The big issue is how do you stop? Because a coefficient of friction of 0.60 is a realistic coefficient of friction between car tires and asphalt. And it would just take too darn long to stop. So kind of a crazy little thought experiment there. 600 meters, like a deer runs out in front of you, you're both in big trouble, right? You need to like pull some evasive maneuver to get out of the way of something, you're in trouble if you're going that fast because you can't slow down, you can't stop. It takes too long. So there's example 4. Give the homework a try from box number, I think we're on box 4. The second day of Newton's laws. You're going to get stuck with some of the questions. Heck, maybe you get stuck with most of the questions. That's okay. You fire me an email, or you save those questions and you hit me up in a Zoom meeting. I would love to see all of you join the Zoom meetings. They really are going to be useful just to talk about some of this information and hear questions and ask your own questions. So please check into those. Good luck with the homework. Don't get frustrated. Again, ask questions, ask questions, ask questions. See you in the Zoom meeting soon.